Okay, let's talk about matter today. We'll talk a little bit the introduction of to chemistry. We'll introduce some concepts that you probably know intuitively, and we'll define them so that they are consistent between people. So anyway, matter, what is that? Well, that's just anything at all that you could see, touch, feel. It's got a mass, it occupies space. So almost everything that you are interacting with is matter. If it's not matter, it's probably energy. So you may feel some energetic field, but that's not matter. So fire, for example, if you touch that orangey thing, that's not matter per se. It's like an energetic thing. It's an emission of light. Light does not matter. Light is more of an energetic type thing. Most other things, your fridge, your table, potatoes and tomatoes and anything like that, that's matter. It occupies some sort of space and it has a mass. All right, we typically divide matter into three states: solid, liquid, gas. The solids, all matter, whatever the material that you're looking at. I don't know, let's say iron or something like that. Iron is made up of these building blocks, and I'll define them in a few minutes. If it's a solid, they're very tightly organized, like in this red picture here. Oops. And because of that organization, solids are very rigid. So any solid you touch has this rigidity to it because of the structure of the matter. And it has some sort of a fixed shape. So if you put a piece of bread in a cup, the bread won't take the shape of the cup. It will just stay the slice of bread that it is, right? And it has a fixed volume to it. Liquid is the building blocks themselves. They're the same. They just got heated up, or maybe they got reduced pressurized or something like that. What's going to happen here is that the building blocks are not as tightly bound to one another, but they're a little more wishy-washy, but they're still pretty close together. So because of that, they're not as rigid as a solid, and they don't have a fixed shape like a solid, but they do have a fixed volume like a solid does. Okay. Gases are free for all. They are molecules. I'm getting ahead of myself. These building blocks are flying everywhere. They're not interacting with one another to a wide degree, and because of that, they kind of take up the space of wherever they are. So, kind of like a little intro there. So you may have heard of other types of terms in chemistry and in physics, and that's substances and elements and compounds. Let's try to get to the bottom of this, okay? So a substance is any sort of thing that has its own properties, okay? And they're distinct and uniform. And what do I mean by that? There are substances and there are mixtures. So sand here, as an example, is a mixture. It's not a substance, because while I call it all sand, the sand in Ormond Beach is not the same as this sand in Daytona Beach. They're a little different. The mixtures are a little different. It's definitely not the same as the sand where I come from on Staten Island, where it's not at all nice compared to the sand that's down here. But even here within two towns that border one another, you could see the variation in the sand. Sand is not a substance. Okay, it's a mixture of different substances. Water is a substance, okay? Meaning that if I look at water in Namibia or Mars or any place at all in the universe, the water will be the same unless it's got stuff in it. But if it's just water, if we're just talking pure water, it will look exactly the same. It will taste exactly the same. It will feel exactly the same. It has the same properties no matter where it is in the entire universe. Sand, not so much. So that's kind of like a distinction here between a substance and something that's not a substance, meaning it is a mixture. Okay. Substances could be two things. So as you can see from the title, I have elements and compounds. Yes, it could be elements and compounds. Elements, they are atoms, all right? And atoms are the smallest units of any substance. So you probably have seen the periodic table at some point, and you could, all these symbols there, they each signify a single atom. So hydrogen is an atom, fluorine is an atom, oxygen is an atom, sodium is an atom. Okay, So if I'm looking at iron, for example, as Fe, as an atom, if I'm looking under the microscope, iron will always look like Fe everywhere. So iron on Mars, iron in Namibia, wherever it is, if I look under a ridiculously powerful microscope, I will see Fe, 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 Fe. I'll see just a bunch of Fe's. They will all look like Fe's everywhere, and they're just one specific element, okay? And then if elements kind of bind to one another in what we call a chemical bond. So I'm getting ahead of myself in the terminology, but we kind of have to use it a little bit. So imagine these atoms start holding hands or something, and they get like into long-term relationships. So imagine hydrogen and oxygen or something. They're getting pretty hot and heavy. H2O would form as an example of something that could form. Lots of different things could form between H and O. But H2O is one type of an example. And that's water. And that is a compound. So O would be an element, H2O would be a compound. So if I can define some sort of any matter in the world, any substance, as these chemical formulas, as H2O or as Fe, or as just, I don't know, sodium metal will be Na, or oxygen gas will be O2, or ozone will be O3. All these things are either elements or compounds, okay? And they have uniform properties no matter where they are and who's looking at them and where they're being looked at, etc. All right, so that's something that just try to wrap your head around that. Let me know if it doesn't make sense there. All right. There is this law of constant composition, and all it says that if within these compounds like H2O or NH3, and it sort of makes sense. H2O, the ratio between H and O is always going to be 2 to 1. So no matter where you look at water, I'm always going to have 2 H's and 1 O. This is ammonia. Wherever I look at ammonia, there'll be 3 H's and 1 N. Okay? Literally, if I started counting them, I would have 1 N, 3 H's for any ammonia that I'm looking anywhere, whether it's in Jupiter or in Pluto. Okay, that's just the law of constant composition. It just defines the fact that compounds have a consistent formula. All right, mixtures. Mixtures, when substances mix, they form these things. They form mixtures, and they are not necessarily going to have. Well, they're not going to have distinct properties. They're not. I can't just mix two things and always say all sand is the same, all milk is the same. It's not. You can have low-fat milk, and I can have high-fat milk. You can have milk from this cow and that cow. It's going to taste like this. It's going to have this sugar content, that sugar content. I can have milk from a camel, milk from a goat, milk from a person. So all these, I call them all milk, but they're all mixtures of fat and water. And there's a whole bunch of different mixtures. And these can be separated physically. So imagine I take, I don't know, sand and, on the beach or something, and I put that through a sieve. Like one of those little filter things that you take to the beach, like a colander or something, and the larger particles would separate out. I'm physically separating things that constitute the sand. Okay, that's a physical separation. All right. If I try to do that with water, to separate that into H and O, I won't be able to do that. I can't physically separate H2O into H and O because H2O is not a mixture. It's a substance. I can separate H2O into H2 into hydrogen and oxygen, but that requires a chemical change. I need to separate it chemically. That requires tremendous amounts of energy that you likely don't have in your own in your own capacity to do. So you can't just take water and separate it yourselves. You have to apply some sort of foreknowledge to do that. Okay. Another example of physical separation would be salt and water. If I mix salt and water in a cup at home, I can separate it back out if I just boil the water. Boiling the water is a physical change too. I'm not changing anything about the water. It's not becoming H or O or something. It's H2O gas. And if I let it sit around for a while, it will condense back and I can drink it. And that's the whole idea behind distillation. I can separate water out of things that have salt in them or other things that are dirty. Okay. All right. So these mixtures, as I'm mentioning, you can physically separate them, not chemically. They're not chemical moieties. They're just mixture. You're just mixing a bunch of different things, and you can certainly separate these mixtures. There are homogeneous mixtures and heterogeneous mixtures. Homo means same, hetero means different. Homogeneous would mean that it acts the same, looks the same, feels the same. No matter where I look at this homogeneous mixture, it's going to act the same as if I look at it somewhere else. What's a good example of that? That would be like juice or something, or sugar water. If you take sugar and mix it with water, say that pretend this is sugar, and you mix, make sure it's well dissolved, okay? And you could leave it there for however long you want, as long as bacteria don't grow in it or something. All right. If I take a straw and I put it right here and I drink, it will taste exactly as sweet as if I put a straw down here and drink, because it's well dissolved. It's a homogeneous mixture. It's everywhere the same. Okay, homo same. And if I look at it in any other way, not just drinking it, if I look at it under a microscope, under some optical method of looking at it and studying it, it's going to be exactly the same properties here as it is here. No matter what way you're going to measure things, it's going to act similarly. Okay, it is not a substance. Again, it's not a substance. It doesn't have its own distinct properties, because I could put more sugar in it and it will still look the same. But it does act the same within this confine. Okay. A heterogeneous, hetero is different, heterogeneous mixture acts differently. So if I were to mix things that are not homogeneous, that would be heterogeneous, I will be able to see differences between different areas. So what's a good example? These things are called, so we're not going to touch this much beyond this slide, okay? But these things are called colloids. And these are words that you're going to be seeing throughout your lives. I want you kind of to think, I won't test you on heterogeneous mixtures per se about this terminology, but I want you to take this away from this, because you won't see it again, and it's important to know this because you will see these words thrown at you. So you've all heard of aerosols, right? You've all heard of emulsions. These things are all types of colloids, and these are all heterogeneous mixtures, okay? What's a good example of an emulsion? Well, milk would be a good example of an emulsion. That's when I'm mixing oil or fat, a liquid fat, with water. So fat and water don't like to mix, as you probably can see through a salad dressing. But if I trick it, I can actually effect this way of creating some sort of pseudo solution, where it looks as though it's a homogeneous mixture, but it's not. It's a heterogeneous mixture. So if you look at milk on the bottle it says homogenized. Okay, the word homogenized comes from this thing. It's being made homogeneous temporarily. Is being made that way. If you leave milk overnight, milk that you bought from the store, you leave it in a cup overnight, you will see the fat go to the top. You just will. If it's fat-free milk, you will see some other junk that goes to the top. It separates. Over time, it will separate. This the homogenization procedure that they create, that they do onto that, is temporary. That's true for any emulsion, any of the things you usually buy for personal use in the shower or something like that, like liquid soap. Liquid soap is a heterogeneous mixture of a bunch of different things, and it will separate. Over time, it will separate. And you can see that a lot of times you get products that separate and they tell you to mix them. And that's because they're not the solutions, they are emulsions or other types of colloids. Aerosols, same thing. Any can of aerosol that you have, you're basically suspending some sort of a solid within air or a gas or something. Over time it will settle to the bottom. So that's why you have to shake the can before you spritz it, because otherwise you won't get the stuff you want out. It settles to the bottom through gravity. So those are that's an example of a heterogeneous mixture. So I want you to, we won't talk about them too much beyond the fact of what they are, but I kind of want you to take that away from this as an enrichment type of thing, because it doesn't get talked about in this course, and I think it's an important facet of physical science that is often skipped. Okay, So here's a picture of milk. Sure. This is an easy way for you to classify for yourselves if you don't like my blabbering. You have matter, which is anything you can see, anything you can touch, anything that you can interact with. And then you ask yourself, can I physically separate it? If you can't, it's going to be a substance. And then, can I chemically separate it? If you can't, it's an element. If you can, it's a compound. So you go back to the top. Can I physically separate it? Yep, then it's a mixture. Is the mixture uniform? Yep, it's a homogeneous mixture or a solution. Is the mixture not uniform? That's a heterogeneous mixture, and that could be a colloid or a suspension. If you want to know the difference between them, let me know. All right, separations. So I am a chemical engineer, as I've told you, and you'll hear a bunch of times. I'm a chemical engineer, and this is one of the biggest realms of what I do, what we do as chemical engineers, is separate stuff. Okay, you may think chemical engineers are chemists. No, that's not true. Chemical engineers are not chemists, but they do deal with chemicals. So one major facet is trying to separate stuff. So originally, chemical engineers would take oil from the ground. So back 100 years ago, so when chemical engineering became a thing, oil from the ground is dirty. It's got a bunch of junk in it, and we don't want all of that. We only just want the stuff that we could put in the car. So we have to separate it. How do we separate it? It's very difficult. So then we use a bunch of these things that I'll just go over very quickly, like distillation or extraction and things like that, to separate stuff into its components. And if you look at chemical plants down over in Texas, where they do a lot of oil extraction from the ground, these huge distillation columns that are, I don't know, hundreds of feet tall, and these big chemical plants, and they just suck stuff out of the ground, and they fit them through these industrial sized drying or extraction agents, and that sort of thing is what chemical engineers do in design. I have a lot of experience with that. If you're interested, let me know. I've taught chemical engineering for all my life, and it's my passion. That's who I am. Mixture, how one can separate it. We discussed distillation. You can distill something by boiling one of say the salt. It's boiling a liquid out of a mixture. You can boil that out. So if you take salt water and you want to extract the water, you can distill the water by boiling it off. You can dry stuff, right? So let's say your shirt is wet. You can take the water out by heating it up, and it will dry the shirt. You can take something that's a little moist and dry it, and you can separate a solid and a liquid that way. There's this thing called extraction. So liquid extraction, that's one example of it. I can have two liquids that are mixed together. I can add a third liquid, and it would make one of the two liquids come out. Okay, and that's called liquid extraction. Right? And there's column extractions, these huge towers that are hundreds of feet tall, and they have inside of them these tiny little beds, or these elements that are meshes or of sorts, right? And then you run things through these columns, and these little mesh things they facilitate an exchange. Let's say I'm moving two liquids past one another in a column. I can make something come out of one liquid and into another. This is one way that we separate, say, carbon dioxide. We try to sequester carbon dioxide out of a flue gas that comes out of a chemical plant, so we don't contaminate the earth further. So you can run something that's very heavy in CO2 through this packed bed, and then the CO2 would get dissolved in, say, water or something like that. Then you can dump it somewhere else that it doesn't contaminate the atmosphere. Okay, and these types of things are called stripping or adsorption. There's other things that chemists tend to use chromatography to separate things. Chemists and also engineers would use filtration, and I think that's pretty, you know, that as a kid. Even you filter something, you put a filter, and then you put something through it, something that's bigger than the filter pores won't go through, right? And then it will stay at the top, and the thing that's smaller is going to go through, and you can separate something that way. There's microfiltration, there's nanofiltration, which is the pores themselves are nano-sized. There's membranes. So you've probably heard of reverse osmosis. Reverse osmosis is a type of membrane that you can push something to separate. Centrifugation, that's something you could see in biology labs, physics labs, chemistry labs, engineering labs, everywhere. That's gravity separating stuff. Something that's heavier is going to come out because of the centrifugal forces. There's other things like chelation, lots of different elements. I'm just touching the surface here. There's a whole lot of different things. While we don't have chemical engineering in our campus, I'll tell you from my own experience as a chemical engineer, as a chemical engineer, I took 2 semesters of classes called Separations 1 and Separations 2. So there's a lot here. I'm just summing this all in one slide, but there's a lot here. All right, we talked about physical and chemical changes. Chemical changes, that's when a substance becomes another substance. All right, so if I take H2O and I try to separate it into H's and O's, then the hydrogen and the oxygen now are separate. They're not water. You can't drink them. You can't bathe in them. They are gases. They're different types of things. And if you try to liquefy hydrogen and oxygen, they won't act like water. It's not water. I separated it, or I changed its identity into a different chemical. That's a chemical change. All right. We call that a reaction. Physical change is much easier to do. It doesn't require as much energy. It doesn't require as much designing and thinking and all this stuff. And that's when a substance just either mixes with something else, or separates from something else, or it changes from liquid to gas or gas to solid or something like that. Right? So if it undergoes a phase change, so if you boil water, that's a physical change. If you freeze water to ice, that's a physical change. If you freeze ammonia, that's a physical change. If you separate ammonia into N's and H's, well, that's a chemical change, because N and H are not NH3. You separate it into something completely different. That's not a physical change. It's a chemical change. It's a reaction. Okay. I take salt. I put it in water. So I mixed it. So that's just a physical change. I didn't change the salt's identity. I didn't change the water's identity, and I can separate them through one of these things. Right. So that's the whole idea there, right? If I separate 2 things that are in a mixture, that's a physical change. If I take milk and I add vinegar to it, and I create and I separate the fat out in what we call buttermilk, that is a physical change. Okay.